the members of the CCMF cohort, as well as members of other cohorts that have joined us today for the first time. Today, Climate Exchange presents a virtual tour of the state-of-the-art carbon capture pilot plant at Imperial College. You'll find out about what a carbon capture plant is and how it works. Our speaker for today is a teaching fellow in the Chemical Engineering Department of Imperial, as well as the manager of the carbon capture plant, Dr. Colin Hill. I'm here with Si Cheng in the plant to help out during the session. And before we get started, it'd be really helpful to kind of tailor the rest of the presentation if we had an idea of the background. So there is a Mentimeter poll with the link should be posted on the chat. If you could just fill that in, and as the results are coming, we get a better idea of the people that we have on the call. But without further ado, I will now hand on to Colin, who will be giving us a tour.
Okay, so welcome to the Department of Chemical Engineering, guys. As Ferdinand said, I'm Dr. Colin Hill. I'm Senior Teaching Fellow in the Department of Chemical Engineering, and basically I'm also in charge of the pilot scale carbon capture facilities that we've got here. In terms of on the briefing that I got, I was told you were all chemical engineers, so I'll just go into the main technical details in this case. No, of course not. What I'll do is I'll bring you up to speed as much as possible, and I do understand you're from a variety of backgrounds. For some of you, some of the things I go through, you may already know. Just to be sure though, I will cover those anyway, and that way I've made sure that everyone's on a similar level in terms of their understanding of the process. In terms of what we'd normally do for this course is actually, I'd get you all to come to the plant area, and I would then do a tour for you around the plant area. So actually you'd be geared up in lab coats and goggles and hats, and I'd take you physically into the plant area so that you could have a look around. Obviously this year that's a bit more of a challenge, and the guys have given me quite a lot more of a challenge because I have to bring the plant to you rather than you to the plant, which means it's a little bit more tricky than usual. Having said that, that's what we'll aim to do over this session. I'll put some of the things you see into context as well, and I know that you've had some talks by various other people to enable you to understand some of the backgrounds of particularly carbon capture type processes previously. So I hope to put some of those into context and actually show you a scale facility that does exactly that. In terms of the image that you're seeing at the moment, this is actually the view that I'm seeing in the control room. So currently I'm in the control room for pilot scale carbon capture process. And in case you're wondering, these are some 360-degree views. I'll move them slowly because I understand sometimes on the bandwidth it's a bit of a challenge to look around. But this is basically my view at the moment. And from here, you can see we've got several sets of displays. That enables me to monitor and control the equipment that you can see in the background. So roughly in the middle of the picture you've got now, if you look through the window, that's some of the equipment that we're operating from the control room. In terms of that process itself, this is a pilot scale carbon capture process. So it's replicating the sorts of facilities that you might use for capturing carbon dioxide from, for example, a coal or a gas-fired power station. It's identical to the sorts of process you use for cleaning up large industrial processes to remove carbon dioxide to prevent it going into the atmosphere. And then that carbon dioxide, once it's been captured, can be transported elsewhere and then either used or stored. So you've probably heard about the sequestration and utilization routes. So we'll touch on those a little bit, but this process is the first part of the CCS. It's the carbon capture plant. In terms of this facility, this is an overview diagram of the facility itself. That goes over 4 levels of the building. So actually the bit that you were looking at through the control room previously is just looking out on the 3rd level of the process. 2 floors below us in the control room, and I'll aim to take you there a little bit later as well, is where we process the liquids. So this level. And the level just above us is where we process the gases so that they can be treated to, on a bigger scale process, so they would be treated to go elsewhere. In case you're wondering how big is this facility, to put it into perspective a little bit, this is equivalent in height to about 3 double-decker buses stacked on top of each other. If you're thinking about how much carbon dioxide would this one capture, if it's running 24/7, this will process around 500 tons per year of carbon dioxide. The columns, the 2 bits in the middle, diameter-wise, they're about your diameter, roughly. Go over 4 floors of the building. That enables us to catch that 500 tons per year of carbon dioxide. In case you want to put that into perspective a little bit, very roughly, each one of you's got a carbon footprint of about 10 tons per person per year. That's around the global average, actually. Depending where you come from, and I understand that several of you will be based in different locations at the moment, but depending on where you come from, that number will increase or decrease a little bit. If you're from the States, we use a little bit more energy, guys. You're looking at about 15 tons per person per year. If you're from China, well, up until fairly recently, China was running at about 4 tons per person per year. But of course, over the last few decades, it's industrialized quite rapidly. They're now running at about 10 tons per person per year. If you're from Europe, again, you're somewhere in the middle, actually, about 10 tons per person per year. If you're Australian, yeah, you've got quite a big carbon footprint, actually, guys. You're running at about 15 tons per person per year as well. Why so big for Australia? Well, for the case of Australia in particular, there's a lot of heavy industry and a relatively small population. That's why the footprint for each person is relatively large. If you remember, I said this facility would process about 500 tons per year of carbon dioxide if it's running 24/7. So this would process equivalent to the CO2 footprint for around 50 people. It goes over 4 floors. It's equivalent in height to about 3 double-decker buses stacked on top of each other. This is a baby, actually. If you look at some of the full-scale processes, and I can send you some more details later, some of the ones currently running are processing around 1 million tons per year, 1.5 million tons per year. So, for example, well, up until very recently, the Boundary Dam's been processing around 1 million tons of carbon dioxide per year. If you're looking at some of the other projects that are online, that have been commissioned, Gorgon in Australia, which is a natural gas processing facility, has been processing now, well, it's aiming to process around 4 million tons per year. So in the grand scheme of things, this is a baby, actually. Now, the way that this particular process works is fairly straightforward, really. This is equivalent to what we call a post-combustion capture process, or actually similar to an industrial separation process. And the way that that works is you have your normal process that generates the energy you need, if, for example, it's a coal or a gas-fired power station. or if it's in a heavy industrial process, it will generate the products and the feeds and things that you need. But of course, when you use the energy on that, the byproducts you get from burning those fuels are carbon dioxide, plus water vapor, plus some other bits and pieces. And what you need to do is catch the carbon dioxide before it goes into the atmosphere, because that's really the big challenge that we're trying to address at the moment. Post-combustion capture is putting one of these processes basically on the exhaust of those big power plants, or at the end of the big industrial processing plants, to prevent the carbon dioxide from going into the atmosphere. So you catch it before it goes to the atmosphere. If you're thinking about why might you do that, well, I'm sure you're all aware that carbon dioxide has got a lot of press lately. It's probably the most famous of all the gases ever. One of the key reasons there's so much focus on carbon dioxide in particular is that it's by far and away the biggest gas that we emit into the atmosphere. And one of the big problems with it is that carbon dioxide traps some of the energy from the sun. So normally the sun would shine down. That energy hits the surface of the Earth, and some reflects back out into space. But if you've got carbon dioxide in the atmosphere, that carbon dioxide traps it, so that instead of that energy going back out into space, it gets stuck close to the Earth. And the big problem with that is that because it's trapping that energy in what's called the infrared part of the spectrum, that means that actually the surface temperatures around the globe are starting to rise a little bit. As a consequence of that, of course, there are various knock-on effects, like things like polar ice caps are diminishing. Since the polar ice caps are diminishing, that has other knock-on effects, because that means global sea levels are starting to rise. And if you think about the consequences of those sorts of things, then actually it doesn't really matter where you are. There are already several countries that are at, or in the not too distant future will be at or below sea level. And if you think about the consequences of that, that means some people might need to change their livelihoods. It could be as simple as people need to go to other places to do fishing and things. In the most extreme cases, though, it could lead to a big displacement of people. And that's really why policymakers around the world are starting to take a lot more notice, because, for example, the International Panel on Climate Change has published some infographics, and I can send you copies of these later, but basically shows that it doesn't really matter where you are. There are already attributable effects to CO2, carbon dioxide. Now, one of the big challenges is actually to ensure that we don't produce too much carbon dioxide and lead to that carbon dioxide getting caught up in the atmosphere. You might be, for the some of the scientists amongst you, probably saying, well, yeah, but carbon dioxide, that's part of the natural cycle. Trees absorb it when they grow. That's true. I mean, as part of the natural growth cycle for trees, they take in carbon dioxide and they generate oxygen. So that's part of the natural process. The big problem that we've got is actually we're producing far more carbon dioxide than the natural environment can cope with. So if you're thinking about how much carbon dioxide does a tree absorb, a single sort of average tree over its lifetime. One of the questions I'd started to gear up before was, what do you think in terms of the amount of carbon dioxide that a single tree will absorb over its lifetime? So if you put some estimates in, then that will get you some ideas. So if you look at those numbers and you start to do things, so you guys should be watching the mental meeting report at the moment for me. Actually, if you look at the numbers that a typical tree absorbs over its lifetime, so assuming a like 40-year lifetime, very roughly, it's of the order of 5 tons of carbon dioxide. If you're thinking about how much carbon dioxide are we emitting on a global basis, that works out to, well, if you look at the numbers, around 90,000 million tons of carbon dioxide per year. And if you think about the amount of carbon dioxide that equates to, if you work it out, it's a big number, but that works out to around 1,000 tons per second. So we've just emitted 1,000 tons. We've just done another 1,000 tons. Just emitted another 1,000 tons. Just emitted another 1,000 tons. And a tree over its lifetime maybe catches 5 tons. That's the magnitude of the problem we're trying to deal with, actually. That means there's not really a single magic bullet for this. It's not a single way of fixing the problem. It needs to be a mix of lots and lots of different things. And that's one of the key bits to bear in mind, really, as you're looking at how do you deal with reducing carbon dioxide emissions. It's a very large number. To reduce it to a sensible value, that means we need lots and lots of different strategies. So all sorts of things have a part to play. Of course, renewables has got a big part. Some countries around the world, if you look at those, I mean, places like Costa Rica, for example, is about 98% reliant on renewables. That's mainly because its natural environment lends itself quite well to using those types of energy sources. If you look at the broader picture on a global basis, actually over 75% of the energy we use is generated by burning coal, oil, and gas. If you think about the renewables, but even the most optimistic predictions, and this is from the renewables guys themselves, say that probably around 15% of renewables will be viable by about 2050. One of the big challenges for renewables in particular, although it's got a very big part to play, is actually about the continuity of supply. I mean, if you're thinking about, in its simplest terms, if you take wind energy or solar energy, very roughly, if the sun doesn't shine, you don't get solar energy. If the wind doesn't blow, you don't get wind energy. But that doesn't matter. I mean, when you're at home, you want to hit the light switch or press the power button on your laptop, and you don't really care about when the wind's blowing or the sun's shining. You just want the power to come through. So that's the big challenge for renewables. It's about continuity of supply. And there are ways of doing that. I mean, some of the research around, for example, the ChemEng department is looking at battery technologies, storage technologies, because they've got a big part to play to ensure we can do that continuity of supply. But if you think about that, how many times have you charged your mobiles in the last week? At least 2 or 3 for sure, even with the best batteries. And that's a little battery. We've got to do this on a big scale. So that's a real challenge for the renewables. And that's why that's one of the key things that they need to address, and the storage technology in particular. Nuclear's got a part to play in reducing that number, that 1,000 tons a second. But of course, nuclear's got a bit of a PR problem. I mean, if I mention to most people nuclear power, although it's actually the safest process industry in the world, when things go wrong, they tend to go wrong in a bigger way. So if I mention nuclear to most people, they'll say, oh, Chernobyl, Fukushima, maybe 3 Mile Island, or nuclear waste. There are ways of dealing with the nuclear waste and ensuring that actually you can use it up as part of the fuel. But not every country around the world is going to be able to use that as a viable energy alternative. If you look in the international energy predictions for that type of technology, again, somewhere around 10% on a global basis. So we've got rid of maybe 25% of all the energy we need. The bulk of the rest of the energy actually at the moment is still by burning coal, oil or gas in some form. And of course, if you burn it, burn the fuel to generate the power and heat you want, then we don't want to put the carbon dioxide into the atmosphere because that's going to be a problem for us. So what we need to do is do it in a much cleaner way. And that's really where technologies like CCS, carbon capture and storage, or carbon capture and sequestration, come into their own. It's part of that mix that most economies are going to need, particularly for some of the larger scale power generation systems, and also for heavy industrial processes, because if you think about it a little bit, even if we get rid of all of the coal, oil and gas that we use for generating power, we still need to heat things. So we've got to generate heat energy somehow, potentially. We might struggle a bit doing that with, say, wind power or solar power. So we need to do those things. But actually, for some of the big industrial processes, if you're thinking about some of the big sectors where you generate a lot of carbon dioxide, actually, things like steel production, cement production, plastics, they're all things we use day to day. And actually, you need quite a lot of energy to generate most of those. If I know that one of the talks you had looked at some more details about, say, how to clean up cement production or how to clean up steel production. All of those types of technology at the moment to reduce the carbon footprint of them need to do it in a cleaner way. And one of the ways of doing that is to catch the carbon dioxide before it goes into the atmosphere. That's what these processes are about, is catch the carbon dioxide before it goes to the atmosphere. And then once you've done that, you can do other things with the carbon dioxide. If you're thinking about some of those bits, how does it all fit together? If I switch across in a moment for you, I'm just going to show you a slide in a second, just to put things into perspective a little bit. But very roughly, that's the sort of way that you'd set things up. So you've got a big point source like a power station or a big chemical processing plant. You catch the carbon dioxide, and then once you've captured the carbon dioxide, you can transport that to where you need to use it or where you're going to store it. The bit in the red circle is basically equivalent to the process that I'm showing you at the moment. Now, the way that that works, the way it catches the carbon dioxide on these sorts of processes is fairly straightforward, really. What we're doing is taking advantage of the properties of carbon dioxide when carbon dioxide gets wet. When carbon dioxide becomes wet, it becomes slightly acidic. So if you remember back to, say, your IB science you did, or your A-level science, maybe, or even your GCSE science, whichever. If you remember back that far, if you've got something that's acidic, you can use an alkaline solution, a base, to react with it to change it into a salt solution of some sort. Well, that's the way the carbon capture bit works, actually. What we're doing is taking advantage of the properties of carbon dioxide when it gets wet. Carbon dioxide, when it becomes wet, becomes slightly acidic. So we can use an alkaline solution, a base, to react with it, to remove it from a mix of other gases. So in the simplest terms, the way these processes work is an acid-base, acid-alkaline reaction. If you remember back all that way to the science you did a long time ago, in some cases, I guess, actually, you could use something like sodium hydroxide, which some of you may remember. One of the problems with that, though, is once you react it, you can't reuse it because it forms a salt. Which, if you're thinking about processing lots and lots and catching lots and lots of carbon dioxide, it's maybe not the best way of dealing with it because you generate lots of another waste product. So what you tend to do on these processes is use a slightly different solution, something called monoethanoamine, MEA, or an amine type solution. And that works in the same way. It's an alkaline solution, but it's got an advantage because actually, instead of the reaction just going one way, this reaction will reverse. And we can change the direction of the reaction by changing the temperature of our solution. So that's a little trick we use, and that's actually partly about why the process is designed in this way, because if you think about that a little bit, if you change the temperature, and you can get the reaction to catch carbon dioxide at a lower temperature, and then release it in a controlled way at a higher temperature, that gives you a big advantage because then you can keep reusing the same solution. You're not generating too much waste, but you're still catching the carbon dioxide. You're removing it from the gases that otherwise would go out into the atmosphere. And that's the way it works, really. What we do is we cycle our liquid in a figure-of-8 loop between the two columns that you can see on the diagram. So the two vertical columns in the middle. For those ones, one operates at a lower temperature. We put our gas mixture into that column and we feed our solution in at the top. So we've got gas flowing up and a liquid flowing down. And inside there, we got the reaction going on. The carbon dioxide gets removed from the other gases and gets caught up in the liquid, actually. What we then do is pump that liquid into the other column. So as you're looking at things, the column on the left-hand side, in that column is heated up, typically to about 110, 115 degrees C, so a little bit above the boiling point of water. And that helps the reaction to reverse. So in there, then the carbon dioxide effectively starts to boil out of the liquid. I mean, because the reaction reverses, it gets released. And that comes off of the top of the column on the left-hand side. So we can then pass that carbon dioxide elsewhere to do other things with it. Of course, we've got to get some heat energy from somewhere. And if you're thinking about the cost of these sorts of processes, from an operational point of view, that's potentially quite a big cost. So if you need to heat stuff, you've got to put energy in. If you've got to put energy in, it's going to cost you something to do it. So one way we reduce that amount of energy that we need is to use the hot liquid that comes out of the bottom of the right-hand column, the left-hand column, which is hot. It's released carbon dioxide. We can use that heat energy, or some of it, to warm up the cold stuff going in. And if we do that, that saves a lot of energy. That means we don't need extra energy. We're taking advantage of the amount of heat that we've already got there. If you're thinking about the process, we're circling it around in a big figure-of-8 loop for the liquids. It's catching carbon dioxide when it's colder. Then once it's captured the carbon dioxide in the column on the right-hand side, that gets pumped across, gets heated up by the hot liquid coming out of the other column, and then goes into the top of the column on the left. In there, the carbon dioxide gets released in a controlled way, so we can do other stuff with it. The liquid that we use in that MEA solution, the alkaline, comes out at the bottom. It's hot. We've got to cool it down anyway because we need it cooler to catch more carbon dioxide. So as we cool it, we can use that heat energy. We need to cool it a little bit more, but then what we do ultimately, once it's cold enough, is put it back into the top of the column on the right-hand side and reuse it again. And we keep doing that lots and lots of times. Of course, we're not necessarily going to get all the energy that we need by doing that. We still need to put a little bit extra in. And in order to do that, well, on here, like you would on a bigger scale process, we use the steam supply, in our case, the college steam supply, to provide the additional heating that we require. If you're thinking about how does that fit together on, so I've shown you on the diagram. If you're thinking about how does it fit together in the sort of simplest possible view, it's basically like this. So we've got two columns. There's the one on the right, which we call the absorber column. That's where we feed our carbon dioxide rich gas in. The liquid we use to catch it feeds in at the top and trickles down through. So that's where we catch the carbon dioxide. The gas that comes out of the top of that column is clean gas, which we call lean gas. That can be released to atmosphere. The liquids capture the carbon dioxide. So it's called a rich solvent. It's rich in carbon dioxide. And we then heat it up a bit and cycle it into the top of the other column. So in there, that's about 110, 115 degrees C. Because of that, the carbon dioxide starts to get released from the solution. That comes off of the top. But of course, I said the temperature was a bit above the boiling point of water. So if you think about that a little bit, well, we might generate some water vapor, some steam from our solution. So that comes off the top. So we now got to separate out that water vapor. And that's what this bit does. The liquid we put back in the column, and the carbon dioxide we can take off and do other things with it. The liquid that comes from the bottom of here is hot. We've got to cool it. As we cool it, we use that heat energy to warm up the cold stuff going in. We then cool it a little bit more and then feed it back into the start again. So that's the figure-of-8 loop. Now, in terms of that part, the bit that you see on the control screens is this actually. All right, so this is the main graphic, and what I'll do in a moment is I'm going to switch across to a live view of the plant for you. So this is actually a live view of the process now. This is what I see on the plant, what I'm looking at on the big screens in the control room. And that figure-of-8 loop fits over the top, actually. So we said we've got one column there. That's the one where we catch our carbon dioxide. The one on the left-hand side is the one where we release that carbon dioxide in a controlled way. And we cycle the liquids in a figure-of-8 loop between the bottom of this one, around, up, into the top of the column on the left. And then the hot liquid coming out of the bottom of there is released carbon dioxide. So it gets cooled down and then goes around in a big circle, gets cooled down a little bit more, and then goes to the top of the column on the right-hand side. That's the basic process, actually. That's how it works. In terms of removing the carbon dioxide, I guess some of you might be thinking about, well, it might be a couple of questions, isn't it? But, and if you've got one, please ask. I mean, I'm sure the other guys will be able to let me know if I don't see it. But if you're thinking about a couple of the questions that might have popped up, well, first one is maybe, why don't we just catch carbon dioxide directly from the atmosphere? Because we've said carbon dioxide in the air is a problem for us. Why do we do it off of a process and not just try and take it out of the air directly? Well, one of the key challenges with that is, if you think about how much carbon dioxide we've got in the atmosphere at the moment, it's around 400 parts per million, which sounds like a big number. It's quite an important number because for most of the models that have been done by scientists around the world, they've said if it goes too much above that, it's quite likely that we're going to struggle to keep our global average temperature within 2 degrees of levels, say, even 50 years ago. So some of the things you might have heard about from, say, the Paris Protocol is we're aiming to try and maintain carbon dioxide emissions to ensure that we don't go above that 2-degree increase in temperatures. So that 400 parts per million is quite an important number, but that's 400 parts carbon dioxide per million parts of other stuff. And if you think about that a little bit, that's quite a small number, actually. It's quite a small concentration. It's quite hard to separate that. You can do it. I mean, there have been some what's called direct air capture processes that have been geared up in places like Canada, for example. So some of you might have seen some of the headlines about those. They've actually made some big advances because they've gone from pilot scale up, and they made a big announcement about a year and a bit ago because they'd scaled things up significantly and they'd improved their efficiency by about 100%. But if you look at the break-even price for that process, they reckoned they'd need to sell carbon dioxide at about $160 a ton. If you look at the current price for carbon dioxide, it's somewhere nearer to, well, $15 a ton. So there's a big difference in that. So that's a big challenge, actually. I mean, they're making big strides, but it's not there yet. If you think about the carbon dioxide that comes out of, say, a big power station or an industrial process, well, very roughly for the gases that come out of the chimney of a coal-fired power station, it's about 20% carbon dioxide in that gas mix. So that means it's much easier to catch. There's just a lot more of it, so it's easier to catch, and that makes it more efficient to do so. If you're looking at a gas-fired power station, it's about 6% by volume. In that particular case, it's a little bit harder to catch, but it's still a lot significantly bigger than 400 parts per million. So it's much easier to try and catch the carbon dioxide before you put it into the atmosphere than trying to deal with it afterwards. Right, so I think that's one of the things to remember from especially if you're looking at the things from the technology perspective and how you can implement it. 2 questions, okay. Yeah, I can't at the moment, guys. Sorry, I can't see the thing. Can you tell me what questions?
So we have.
Wait, never mind. I'll just tell you. So the first question is from Asta. Where does the CO2 process come from? The one in the Bible.
Okay, where does the CO2 process? Okay, good question. So the CO2 plant that we've got here, this is actually one that we designed and built in-house. From our point of view, it's much more about teaching, actually. So one of the big parts for us is, of course, it's good to have all these facilities in place and to gear them up, but you need people who are capable of operating them as well. And one of the reasons we geared this one up is so that we could train our students and get them familiar with the sort of processes they're likely to use later. In terms of the technology, this is based on quite an old technology, actually. So this is something called gas sweetening process. If you look through the patents for that, that technology was developed in the late 1930s. It's just not been used in quite this way before. It was used for removing acidic gases from methane and so on. So things like hydrogen sulfides and so on. More recently, it's got adopted for that technology. So actually, there's quite a lot of experience there. It's not like some super fancy new technology that no one's been tested before. It's not been used in exactly the same way before, but there is a lot of experience there. So, first question. Next one.
We have a question from James. James, are you able to ask your question?
So he's asked about nuclear fusion. Do you think?
Okay, yeah, good. Yeah, I mean, I said that nuclear power would take the predictions. If you look on the International Energy Agency predictions, it says nuclear will account for about 10 to 15% of the global energy mix. Of course, the key way of generating nuclear power at the minute is fission, so breaking stuff apart. There's been quite a lot of work on looking at fusion, so that's joining two components together. And when you join those molecules together, those atoms together, in principle, you can generate energy. One of the big challenges with that at the moment is fusion started to get developed in the, well, about the 60s. And the statement at the time was nuclear fusion would take over within about 30 years. There's been a lot of advances on it, but if you ask the nuclear fusion guys at the moment, when will it be viable as an energy resource? If I asked them 10 years ago, they'd say, oh, about 30 years. If I asked them tomorrow, they'd say, oh, about 30 years. There's still a lot of challenges on that one at the moment. Not to say it won't have a part to play longer term. Is it going to fix some of these problems immediately? I think if you're looking at it that way, well, as you know, several economies and several big companies have already committed to net zero by 2050. In legislation, I mean, UK actually was amongst the first of the big industrial nations to do that. When Theresa May made that announcement, that was on the pilot plant here actually. So she was stood in front of the columns that I showed you and said, yep, the UK is going to commit to net zero by 2050. Of course, prime ministers change, policies change a bit, but actually a couple of weeks ago, we had Alex Sharma here. And in case you don't know who Alex Sharma is, he's the Minister for BEIS, the Business, Energy, Industry and Strategy Department in the UK government. He's also actually currently the chairman of the next Conference of Parties meeting. So in November, there's scheduled to be a meeting, a global meeting in Glasgow, or well, virtually in Glasgow, I don't know yet, which is equivalent to the Paris Protocol. He's the chairman of that. So he came a couple of weeks ago. And as part of that, that was tied in with releasing the white paper that the UK government have done to commit to how they will actually try to achieve that net zero by 2050. If you're thinking about some of the other economies around the world, well, China, end of last year, committed to net zero by 2050. So no CO2 emissions by 2050 overall. Of course, America had a slightly different view on things until fairly recently. But actually, even within the last few weeks, America's position has shifted as well. They're starting to move towards net zero by 2050. If you're looking at some of the big companies, GM, car manufacturer in the States, they've said they're going to shift their car production to be all electric by 2030-ish. Most economies are saying similar things. They're going to aim for all electric cars by 2030 because actually that's got a part to play as well. Fusion, we said, is probably 30 years away. It might get there by 2050, but is it going to help in the immediate term to reduce those CO2 emissions? A bit more debatable, I think. So one of the things we need to look at a little bit is how can we use some of the existing technologies we've got to go a big way towards reducing those CO2 emissions. And if you remember, I said 1,000 tons per second. So it's quite a big challenge, actually. It's not a trivial thing. It's not like we get a single magic bullet and it fixes it all, unfortunately. It's going to need to be a mix. Different economies need to do it in different ways because their energy mix is different. The way their economies are driven are slightly different. But things like CCS, for sure, has a big part to play. If you look at, even over the last year and a bit, 2 years, there's a lot of big projects gearing up now. So there's a project called Gorgon in Australia. That's actually gone through commissioning. It's catching carbon dioxide from methane to reduce the amount of carbon dioxide in the methane. That's catching about 3 million tons per year of carbon dioxide. There's projects gearing up in Brazil. So off the coast of Rio, actually, near to the Campos Basin. That one's catching about 2 million tons a year of CO2. If you look at China, they're doing similar things. If you're thinking about the UK perspective, actually, there's a couple of big projects gearing up there. One of them is Drax Power Station, which is actually the biggest power station in the UK, is looking to generate its energy by burning biomass. And if you think about that, well, one way you can generate energy is to burn coal, oil, or gas. But another way is if you use plant material, and you think about that, while the plants are growing, they take carbon dioxide out of the atmosphere. It's part of their natural cycle. If you then burn that plant material to generate the power and the heat that you want, and you then catch the carbon dioxide, and you store the carbon dioxide underground, actually you've achieved the equivalent to removing carbon dioxide directly from the atmosphere. That's something called BECCS, bioenergy with carbon capture and storage. And we said the whole key aim was to stop the carbon dioxide going into the atmosphere. So that achieves it for sure. In terms of putting it underground, why do that? Well, actually, there's quite a lot of storage capacity for that. And if you pump, there's certain rock structures that lend themselves quite naturally to catching a lot of carbon, to storing the carbon dioxide and keeping it there over geological times. If you're thinking about that one a little bit, the rock structures actually allow you to trap the carbon dioxide, store it, and over long time periods, then the carbon dioxide becomes part of the rock structure, so it traps it in place. That's actually the way that most of the biggest processes around the world are working at the moment. In terms of, if you're thinking about some of the other areas, there's a project gearing up to a place called Northwich, run by Tata Chemicals. That's taking carbon dioxide from a combined heat and power process, catching it, and then converting it and using it for changing it to use as a feedstock for sodium bicarbonate, which is used for the glass industry a lot. So there are uses as well, but the thing is, the uses tend to be relatively small. At the moment, the best way of dealing with things is to store it underground. Okay, you want to see a bit more of the process? Okay, I'm getting messages over here. I've got the guys tapping me on the shoulder. Okay, so in terms of the process itself, the bit you can see is the control room. What I'm going to do for you in a bit is actually send you some links, so you will be able to look around the process. But in case you're wondering what it looks like in the plant area, this view's got some hot links, and actually if you click on the pluses, that lets you go to different levels of the process. In terms of, if I click on the bottom one, because that gets you the best overview, what you will see is, I've preloaded it in this case, but what you will see is we can go into the ground floor of the plant area, and I can make that bigger for you. This is a bit like Google Street View, basically. We're actually using better cameras than Google use. It's the best technology available, honestly. So if you want to, with the links, what you will be able to do is drag the images around. And I'm watching because I know there's a bit of lag on this. So you can do this full 360 view. You can look around, you can see all the components. And like on Google Street View, you can move around to a different location. So I've just clicked. So now we're looking in a different place. So you can do the walk around as well. And if you start to move it around, you can then look at the process on the ground floor. So this is you on the ground floor now. As I said, I'll send you the link so you can actually do the look yourself. So I'm now looking at the process front on. In the background, you've got the two vertical columns. And in case you're wondering, do they go all the way to the top? If I move the image a little bit more, I start to look up. Actually, you can look up to the floor above. And you can see all the way up to the very top level. So I think that puts in perspective a little bit for how big this process is. And remember, I said it's a baby, actually. If you want to look in a little bit more detail at things, you can do the walk around exactly like you would with Google Street View. So very roughly, in our case, we're feeding the carbon dioxide, the mix of carbon dioxide in on the bottom right-hand side. So where you can see the tank labeled up is F100. To the right of that, there's some small pipes. That's where our gas feeds in. That's the mix of carbon dioxide and other gases that we're using for our purposes. That goes into the vessel on the right-hand side. So if you look to where you've got the blue vertical line, the blue vertical beam, to the left of that slightly, there's another small vessel. It goes into there. From that one, it then feeds into the bottom of the column on the right-hand side. So I've now swung the view around for you a little bit. So of the two columns, there's one on the left, one on the right. Our carbon dioxide feeds into the bottom of the right-hand one and then flows from the bottom all the way up to the very, very top floor. The liquid we use to catch it feeds in at the top. So that's what some of the pipes are showing. Sorry, my cursor's not moving very well at the moment on this, but basically the liquid feeds in at the top just here. That's where we catch the carbon dioxide. The clean gas, in our case, comes off of the top of that column. And we want to reuse it. So we cycle ours back through one of those vertical pipes back to the start again, because we want to reuse it again. The liquid, though, that comes from the bottom of that column goes from the bottom and then gets pumped through. There's a blue rectangular frame near to the back. That's where we heat up that liquid and start to heat it. It then goes through the big diameter silver pipe. So you should be able to see my cursor now because it started moving again. So it goes up through there. That's hot. It feeds all the way up to the very top of the column on the left-hand side and then trickles down through. And as it does that, as it goes down through this column, the carbon dioxide starts to get released because of the temperature. So carbon dioxide goes up and the liquid goes down. Carbon dioxide that comes off at the top, what we can then do is separate that off, make sure it's dry. And again, we want to reuse it in our case. So we cycle ours back to the start again. On a big scale process, that would get used elsewhere. So if we went to, say, the top floor, so at this time, if I go back to the plant diagram, instead of being on the bottom floor, we're going to look on the top floor where the gases get processed. This is the top level. So if I go to the far side, this is the column. So the column that you can see there is the one on the right-hand side as you were looking before. So left-hand side as you were looking before. That's the hot column. That's the one where we release the carbon dioxide from our solution. The one on the far side is the one where we catch the carbon dioxide. From the top of this one, we've got the gas that comes off. That's cleaned up gas. In our case, mainly nitrogen, but it might have a few liquid drops in because of the way that the liquid flowed against the gas. So we pass it through this vessel, which is a separator. Any liquids, droplets that were caught up in the gas get separated off and they get put back into the top of that column. The cleaned up gas, the nitrogen, comes off at the top and then goes through that pipe towards the back where actually we can release it to atmosphere or we can reuse it. That's the clean side. For the hot column, what we call the desorber or stripping column, that's the one that allows us to release the captured carbon dioxide in a controlled way. Because of the temperature, carbon dioxide comes off at the top. And actually we'll get some water vapor as well, if you remember. So what we need to do is we pass that mixture into this vessel. That separates out the water vapor to dry it up a little bit for us. And once we've done that, what we then do is, if I go a little bit more into the plant area, and look across. So if I spin it around a little bit, you can see a little bit closer. So our carbon dioxide comes into that, gets dried up a little bit more. And then any liquid that's left over goes in the small pipe and goes back into the column. But the carbon dioxide goes through this pipe and then back down to the rest of the process again. Any other questions at the minute, guys? As I said, I'll send you the links for these through Sweetening and Ferdinand. So actually you can have a look around on your own a little bit later. And basically do the equivalent of walking around a carbon capture plant. As I said, this is a relatively small one in the grand scheme of things, but nonetheless, it goes over 4 floors of the building. So saves you walking up and down 4 levels of stairs, put it that way, guys. Yep, any questions you got, guys? If you want to ask, then I guess we'll go for the questions.
Hey everyone, thank you so much again for
Hope you learned a bit more about the role of CCS, why it's so important, and hopefully you got a bit of an idea as to how you could kind of get involved. We are aware that there are a number of questions still in the chat, but as we're over the hour now, we would look to get those answers to you via email, if that's okay. And at this point, we'd just like to thank Colin so much for his time and wonderful talk. If you're able to please give him a round of applause for his time, we'd very much appreciate that.
It's a bit strange because
You're muted.